In this video, I'm going to go through some slightly more challenging examples of optimizing the values of absolute value of z and the argument of z given a complex locus in the plane. So the first example I've got has a circle, which unfortunately doesn't touch any of the coordinate axes. But we can still do these four values if we know enough information. So we're told that the center is 5 plus 12i. That's also given from the expression up here. And the radius also is 6. I'm not going to draw that on the circle, however, because I don't want to get it in the way of the picture. So we're going to start off by doing the maximum and minimum values of the absolute value of z, because that's easier to do. So we'll do max of mod z and minimum of mod z. Okay, so no matter where the circle goes, the way to figure these things out is normally to join the center of the circle with the origin, because we're doing distances to the origin, and that's going to be the line that's going to help us get those. So I'm going to firstly join through here. Okay, the reason why this works is because it approaches this circle perpendicular to the tangent like that. So it's going to give us the smallest absolute value there and the largest over there. Okay, so how far away from the origin are these points then? Well, if we know enough about the circle, we can work this out. So if the center's at 512 in terms of a coordinate, so we can get the modulus of the center point, that's going to be 13. And then if the radius is 6, I'm trying to draw these braces upside down, there you go. Then we can add and subtract 6 from 13 to get these maximum and minimum values. So clearly from the picture we've got the maximum value is 13 plus 6, that's 19. And the minimum value is 13 minus 6, which is 7. Okay, so that's fairly straightforward. Okay, the tactic there is normally the same as to draw that line through the center of the circle. All right, for the argument then, I'm going to need to maybe draw around this picture and draw it again. So if I get rid of these colours as best I can. Great. Okay, so the maximum argument then is going to be what I get if I rotate round anti-clockwise as far as possible while still remaining on the circle. So that's going to give me a point up here with the maximum argument. That's tangent on the left. And the minimum argument is going to be tangent down here with a smaller argument there. Okay, so now what we're doing is we're aiming to make a kite by joining the tangent points over to the center of the circle. So here we go. That's obviously going to have length 6 because of the radius, and same down here. And that gives us a kite to work with. Okay. Now, eventually, we'll think about what angles we actually need to get. Now, last thing I want to draw on the picture is going to be the line that joins the origin back to the center again. Okay, because that splits into two congruent right-angled triangles I can use to get some angles going. Okay, so let's stick an angle in here. Okay, we've worked out that the radius is 6. I can put that on there. It's the same over here. And also, we also worked out that the hypotenuse of this triangle is going to be 13 because that's the absolute value of the center point. Okay, so let's maybe draw that triangle out again and I can figure out alpha, bearing in mind that it's the same alpha in there because the triangle's congruent. Okay, so here's my triangle, 6 here, 13 here, and here's alpha. So alpha is clearly going to be inverse sine of 6 over 13. Okay, now we're normally working in radians, so I've done this in radians, and that gives me alpha equals 0.480, and that's to 3 decimal places. Okay, so that gives us quite a lot to work with in terms of working out these blue arguments here. But what I really need is I need the angle that gets me onto the first tangent line here down at the bottom. So if I can use another triangle, I can join the center point down to the real axis. And then that allows me to get the angle that goes in here, which I'm going to call it gamma. Okay, so looking now in this kind of red right-angled triangle, I can get gamma using some more trigonometry, and then that allows me to add and subtract to get the final values, which is what I want for maximum and minimum for arc of z. So let's draw our red triangle again. So here it is. it joins the origin to the centre, which is at 5 plus 12i. And here's gamma. So using tan this time, so gamma is going to be the inverse tan of 12 over 5. And that's going to give me 1.176 radians, like that. Okay, I should probably have specified radians on this one as well. Okay, great. So now that's everything I need to get these values that I need, finally. So the minimum value of argz, well, that's the angle that I turn through to get to this first line here. So that's going to be this angle down there. And that's going to be gamma minus alpha. Okay, gamma minus alpha is going to be 0.696 radians, okay, if you subtract these two. And then the maximum value, well, if you look at the picture, that's gamma given there, plus this extra alpha on this left-hand portion there. Okay, and if you work that out, that gives you 1.656 radians. Okay. Right, so that's the general method there for getting those 4 values for any given circle. Okay, that being able to draw the correct triangles on is going to be useful to you there. Okay, finishing off then, I've got a second example that's got a line locus this time, and I want the minimum value of absolute value of z this time. Bear in mind there is no maximum value because this extends off to infinity in both directions. You're not going to get a maximum value. The line though is 3x plus 4y equals 5. So if I want the minimum value of the absolute value, then the shortest distance to the origin will be given when I'm at a right angle to this line. So if I join the origin here at a right angle, then that's clearly going to give me the shortest possible distance to that line. Okay, so it's this distance here that we're after. Now, because we've attached to the origin, it gives us a bit of information about the nature of this red line. So firstly, I know that this is going to be of the form y equals mx. I know that because it goes through the origin, it has no plus c. And the value of m is going to be the gradient perpendicular to the line that I've got. Okay, I'm just going to put that perpendicular symbol there. I'll put the line there. Locus. All right, so if I can work out this gradient, I can work out this line and then figure out the distance between the origin and the intersection point there. So let's rearrange our lines equation and figure out its gradient. So 4y equals minus 3x plus 5. And then y equals minus 3/4 x plus 5/4. Okay, great. So now I know that the gradient of this locus line is minus 3/4. If I then negate and flip, I can get the perpendicular gradient, which is then going to be 4/3. So I now know that this red line has equation y equals 4/3 x. Great. Okay, now what it remains to do is find the intersection point, which I'll call x, and then I want the distance from the origin to x, which can easily be done with Pythagoras. So I'm going to get rid of this to have some space. So now I'm solving a system of equations. So y equals 4/3 x meets y equals minus 3/4 x plus 5/4. Okay, equating the two gives me this equation. And I'm going to immediately add the x's over to this side as well, just to save time. Okay, that's by combining these two. Then if I multiply by 12, that's going to clear away these 3's and 4's in the denominator. So I'm going to do that. So times by 12 and times by 12. That saves me combining and making a common denominator. Okay, so timesing this by 12 is going to give me 16x. This one timesing by 12, it will give me 9x. And this one timesing by 12 will give me times 4 times 3 is 15. Okay, so 25x is 15, which means that x is 3/5, 15 over 25. But then y is 4/3 of that, so 4/3 of 3/5. If I divide it by 3, I get a fifth. If I times it by 4, I get 4/5. Okay, so now I know the coordinate of intersection. That's what x is. Capital X, and then its distance to the origin is what I'm after, the minimum value of arg z, mod z. So these are the components. If I put them into Pythagoras, I can get the answer. Okay, and I'll leave you to check that that equals 1, just to finish off. Okay, that's my final answer. All right, great. So hopefully those brought back some fond memories of when you did this first time around in year 12. If you need any extra help, then please feel free to give me an email, because I'll be more than happy to help you with any other questions that you might find. Otherwise, best of luck. I hope you succeed with today's work. Thanks, year 13. See you soon.